Now we're going to look at temperature and heat. The objectives for this part of the session, I want you all to be able to give a definition of specific heat capacity, explain the difference between the different types of heat transfer, and recognise the relationship between Celsius and Kelvin and the scales that they're measured on. Temperature can be measured in a variety of scales, but in Britain we generally use Celsius. Some people might call it centigrade. And this temperature scale is based on one of the most common substances found on Earth, which is water. And at 0 degrees Celsius, water will freeze, and at 100 degrees Celsius, water will boil. There are other scales, for example, Fahrenheit. They used to use Fahrenheit in the UK, not anymore, and they do still use it in the US. And Kelvin, and the proper scientific measurement of temperature is Kelvin. The interesting thing about Kelvin is that actually each unit of measurement for Kelvin is exactly the same size as the unit of measurement for Celsius. The difference is that they are offset scales. Celsius is based on the freezing point and boiling point of water, whereas Kelvin is based on what's known as an absolute scale of temperature. 0 degrees Kelvin is the coldest that it is possible for it to ever be. And it's worth noting that, as I've said, each unit of measurement is exactly the same size for Kelvin and Celsius. If you go up 1 degree Kelvin, you go up 1 degree Celsius. If you go down 1 degree Kelvin, you go down 1 degree Celsius. If you go up 100 degrees Kelvin, you go up 100 degrees Celsius. But the scales are offset. 0 degrees Kelvin starts at absolute zero, which is minus 273 degrees Celsius. So therefore, when you get up to 0 degrees Celsius, that would then be 273 degrees Kelvin. When it comes to measuring temperature, to measure temperature we'll need a thermometer, and there's various types of thermometer. You might use a digital thermometer for measuring the water temperature at taps, for example, or measuring air temperature even. But then you might also use clip-on thermometers, which would clip around pipes for measuring flow temperature and return temperature. There's a very useful tool called a differential thermometer, which you can clip onto one side onto the flow, one side onto the return, and that'll actually tell you the difference, work out the difference for you between those two pipes or surfaces, whatever you've fixed it onto. Excuse me. Now we're going to look at heat transfer. Heat will always transfer from an area of high concentration to low concentration. Essentially, heat will always go from hot towards cool. And there's three main ways that heat transfer can occur. These are radiation, convection, and conduction. Radiation is the only type of heat transfer that doesn't actually need any material medium to transfer. It doesn't need any molecules to travel through. It can travel through a vacuum, and that's how heat from the sun comes to the earth, essentially. And radiation travels in waves, and these waves travel in straight lines. Generally speaking, light-coloured and shiny surfaces will reflect radiated heat, whereas dark-coloured or matte surfaces are more likely to absorb the heat. Convection now. Convection will only happen in fluids, for example, gases and liquids. Essentially what happens is, as these materials are heated, the molecules will become less dense, they expand, just like anything does when it's heated. Generally speaking, things will expand when they're heated. And this is actually the key to what allows convection to actually happen. These molecules, as they're heated, they become less dense, so therefore the cooler molecules fall down in between them, pushing up the hotter, less dense molecules, which then is part of the reason why we say heat rises, but it'd probably be a little bit more accurate to say that cold falls. But yeah, that's, in a nutshell, that's how convection happens. The hotter molecules become less dense, and the colder, more dense molecules fall in between them, pushing them up. And then we get the heat sort of rising up, and then as it starts to cool, it starts to fall down again, and you can end up with a cycle occurring. Conduction happens in solids. Essentially, as you heat up an object, the molecules will start to vibrate and bump into each other, and that is how the heat is then transferred from one molecule to the next. It can also, and does also, cause thermal expansion, which we're going to look at pretty soon. Metals are very good conductors of heat and electricity, and non-metals like plastics are generally good insulators. Excuse me. One of the other properties of metal that makes it a good conductor of heat, as well as making electrical conduction possible, is that there's many free electrons which travel through the material, bumping into the other atoms and speed up the heating process. And as I've said previously, copper is a particularly good conductor of both heat and electricity. And whenever you have heat transfer taking place, very often more than one of these methods of heat transfer will be taking place. And you can see from this picture here, you can see you have a fire here which is giving off radiated heat. The heat from the fire is being conducted through the metal into the water, and then within the water, within the fluid, we have convection taking place. We'd also have convection taking place as the air is heated as well. So we've got conduction happening through the solid, convection happening in the air and in the water, and radiation with some heat being coming off from those flames as radiated heat. So now we're going to talk about specific heat capacity. You can actually work out how much energy it's going to take to heat a substance using their specific heat capacity. And the definition of specific heat capacity is the amount of heat energy required to raise 1 kilogram of a substance, of a material, by 1 degree Celsius. Or Kelvin, because they're both the same unit size. Simply put, you'd need 3 pieces of information to work out the amount of energy, the temperature rise in degrees Celsius or Kelvin, the mass of the substance in kilograms, and the specific heat value, which is measured in kilojoules per kilogram per degree C. So the calculation you do is specific heat value times mass times temperature rise, and that gives you an answer in kilojoules. And this is the common specific heat values for some substances like water, aluminium, cast iron, zinc, copper, mercury, lead, and gold. The key one really to focus on is water, because obviously as plumbers, as heating engineers, that's sort of often what we need to heat. So you can see the specific heat value for water is 4.186 kilojoules per kilogram per degree C. So that's how much energy it would take to raise 1 kilo of water by 1 degree C, or by 1 Kelvin. So the example calculation we've got, if we were to raise 5 kilograms of water by 3 degrees Celsius, essentially we would multiply the mass of the water, which is 5 kilograms, by the temperature rise, which is 3 degrees, times the specific heat value, which would give us an answer of 62.79 kilojoules, or 62,790 joules, because kilo just means 1,000. Okay. If we wanted to raise the temperature of 5 kilograms of copper by the same amount of temperature, we'd do exactly the same calculation, but we're just substituting the specific heat value of copper for that of water. So 5 kilos of copper raised by 3 degrees C. So 5 times 3 times the specific heat value of copper, which is 0.385. And we multiply all of those together, which gives us 5.775 kilojoules, or 5,775 joules. So you can see it takes a huge amount more energy to heat water than it does copper, which actually makes it quite a good heat transfer medium, because once it's heated, it actually stays hot for a moderately long period, and it makes it really useful in our heating systems to transfer heat from the boiler out to the radiators. It takes a lot of energy to heat it, but then once it's heated, it stays hot and can be transported around the circuits fairly easily. Now it's time for your task.